So the first thing I wanted to talk about in this bit of the lecture is Merkle trees. Now remember, Merkle trees are an interesting part of computer science and mathematics, but really the main point here is that they are a device to ensure an immutable record on the blockchain. So as part of this, it's a slightly unfortunate name, but you introduce a cryptographic function, just a rule called a hash. And what we mean by function can sound a lot more complicated than we really mean. So a function in this case is just a rule taking two numbers as input and producing a third number as an output. So as part of this discussion, you don't need to know what precise functional rule the hash is, it's just some rule. So in go two numbers and out goes another one. So again, a function is just a rule, in goes two numbers, out comes another one. So given two numbers, h3 and h4, so the hash function of h3 and h4 is just another number, h1. Okay, so the hash function is just a functional rule mapping these two inputs here, h3 and h4, to another number, and output here, h1. Okay, so you've just here got a standard algebraic procedure like you would see in everyday calculations. It just has to be more abstract because this is something that you're ultimately going to program into a computer. So a Merkle tree is an interesting thing in terms of computer science and mathematics, but here all it is just an abstract device in order for you to be able to obtain an immutable record of transactions onto a blockchain. So we've got a picture of a Merkle tree on the next slide. So the idea is that the following Merkle tree shows that if you change, say, the entry h0, then you'd have to change all the record below that. Okay, this is precisely because the numbers h0, h1, h2, h3, h4, h5, h6, data 1, data 2, data 3, data 4, etc. are all chained together as part of a sequence of complex calculation. Okay, and as I said before, the name blockchain comes about precisely because you have blocks of transactions in this way, all chained together through Merkle trees on this blockchain. Okay, and then as we said before, there's two fundamental guiding principles behind the blockchain. The first thing is trying to establish trust in a trustless environment, and then the second crucial thing here is perhaps not to avoid an attack completely, but to make it computationally expensive. So if you're trying to pick off one node here, h0, you've instead got to actually attack all these nodes here, h0, h6, data 1, data 4, all together. So this is an illustration of a Merkle tree then, and again this is an interesting thing in terms of the underlying computer science theory and mathematics, but really what we're interested in today is that this is just a abstract device in terms of trying to obtain a immutable record of transactions on the blockchain that it is too computationally expensive to attack. So I think the basic way of looking at this picture is to look at the top and work your way downwards. So suppose you wanted to attack the node h0. So this is related to h1 and h2 from the hash function, so you'd have to attack the second layer as well, and then indeed in order to attack h0 you'd have to attack the level below that, and indeed the level below that. Okay, so what you're trying to do here is chain blocks of transactions together, and remember the fundamental aim here isn't necessarily to avoid an attack completely, it's just to render it computationally expensive. So if you wanted to attack the node h0, instead you'd have to attack the whole of this subnetwork. Okay, so you're not saying to somebody attacking the network, it's not impossible to do this, it's just going to be computationally expensive to do so, and you better pick on somebody the right size. So as constructed then, Merkle trees constitute a defense against what is termed a denial of service attack. So a denial of service attack, the idea is if you spam, say, a web server repeatedly with mundane requests until the system overloads and fails. So this imposition of a proof of work, here illustrated using the hash function, makes sure that the outputs from various nodes have to match. So the basic idea is, again, not to avoid attacks completely, just to render them computationally expensive. So because you've got this sort of proof of work and the hash function, the idea is that you can slow attacking machines by increasing the number of calculations involved, and hence the computational burden on attackers. Okay, so if you saw the previous example, if you wanted to, say, attack the node H0, you'd simultaneously have to attack all of that little subgraph. Okay, so I think this is sort of useful in terms of the philosophy of how these things are constructed and what the guiding principles are. You're not really trying to avoid an attack per se, you're just trying to render it computationally too expensive. So another thing that goes with these Merkle tree structures is a need for something called a proof of work concept. So you need both together, a proof of work concept and a Merkle tree-like structure. Otherwise, cyber criminals could eventually just recompute the entire tree and insert fraudulent entries. Now you can think of the Bitcoin blockchain as reporting about networks purely consisting of zeros and ones, signifying the transfer of funds. Okay, and in other cases you might see the word value used in relation to networks, and what you really mean by value is, in more abstract terms, information. Okay, so if you think of these things in terms of transferring information rather than just value, you can hopefully see that it's possible to construct blockchains using non-financial data. So the point here is that you start off with something that originated as just the sort of technological skeleton behind Bitcoin, but instead you can have something that's equally applicable to non-financial data, and some example applications might include clinical trials records, tracking food supply chains, and indeed other supply chains, and land registry records. So in each case, what you're fundamentally trying to do is ensure trust in a supposedly trustless environment. So the next thing that's important with regard to the Bitcoin blockchain is this notion of mining. Remember that what this is trying to do in terms of the Bitcoin currency is provide an analogous process to the process of mining for precious metals when you've got a conventional currency in historical times. So in terms of mining, what's going on is that suppose you offer somebody a fee for the first person to correctly calculate a block of unrelated transactions. So this is intended to act as an incentive for somebody who's got computational resources and cheap electricity available. This mining fee is then intended to incentivize thousands of people to load software onto machines to conduct the complex checks necessary in order to make the blockchain run. Okay, so there's an analogy between this process of Bitcoin and blockchain mining and the use of freeware software to detect bugs. Okay, now implicit in this can be quite subtle. There is a trade-off between blockchain security and the production of an immutable record of data that nobody can dispute versus computational costs in terms of the electricity consumption required. So there can be quite a sort of subtle environmental cost to these things precisely because of the electricity consumption needed in order to run these computational tasks. So blockchain mining then, as we discussed before, builds on this sort of legacy of distributed computing, and often you find that if you have freeware, such as R that we saw earlier in this course, this is in some ways more robust and more flexible than other software constructed under a different model. So there's this legacy of open source computing and distributed computing, and grand scale projects that fit in with this are things like the search for extraterrestrial intelligence unfolding at home, whereby what you do is give individual volunteers a piece of code to run in the background when their computers are running but idle. So in terms of the search for extraterrestrial intelligence, what this is doing is running software for astrophysics programs, for folding at home project. What this is doing is conducting computational studies of protein folding with medical applications in mind. And so the related idea with blockchain mining is to similarly incentivize thousands of individuals to contribute to a complex computer network. Okay, but it turns out that possibly a more concrete analogy to draw upon here is this model of open source software. Now, within this general way of operating, blockchain mining is potentially a bit different for Bitcoin, precisely because Bitcoin is designed as a currency and indeed as a specialist financial application of blockchain. So the Bitcoin blockchain then is different due to its specific financial motivation. Firstly, in terms of a response to the crash of 2008. Secondly, is response to the progressive devaluation of national fiat currencies. Classic examples would be the US dollar or UK pound sterling. So Bitcoin, as part of this, includes an ultimate supply limit of 21 million Bitcoins. So the idea here is that this imposes a scarcity constraint akin to the limited supply of precious metals like gold and silver that historically underpinned national currencies. Now, within this explicit design, the true level of Bitcoin scarcity is likely to be even higher. So, for instance, lost Bitcoins. So, for instance, if you forgot your cryptographic key to unlock your money, have you made the ultimate mistake and thrown out your old computer and the old computer hard drive that had your data and your money on it? Okay, so there are two things here that Bitcoin seeks to mimic: a scarcity constraint and this sort of mining process. So remember, the whole point about blockchain is to try and establish trust in a potentially trustless environment. Think back to the Byzantine generals problem. Now, in terms of the financial and economic aspects of cryptocurrencies, national currencies like the US dollar or UK pound sterling involve a lot of implicit trust in national governments and national institutions. And indeed, the classic example here for finance would be the US government and US dollar, reflecting that much of modern finance is inevitably US centric. Now, perhaps individuals may ultimately like to place similar levels of trust in cryptographic technology, and this sort of blockchain way of establishing trust in a potentially trustless environment. And there's another way in which cryptocurrencies could potentially reduce financial risks, and there's sort of a long-standing need to solve problems relating to the transfer of money across borders, circumventing multiple layers of middlemen and antiquated money systems. So as part of that, I can remember being flabbergasted to hear that cheque payments in the UK until very recently relied on the postal service, for example. So there's a genuine technological demand, I think, that Bitcoin and cryptocurrencies potentially solve in terms of the transfer of funds across borders, but some have also pointed to a potential association between Bitcoin usage and criminal activity. So one important thing to say here at this juncture is that blockchain and Bitcoin and other cryptocurrencies are potentially vulnerable to a whole host of technological developments. So research at the interface of finance and psychology, indeed in particular neuroeconomics and finance, suggests that all financial decision making contains an emotional component. Indeed, from an evolutionary perspective, emotions might have evolved and might be important to assist as a safeguard in complex decision making. Ultimately, therefore, people have to make a fundamentally emotional decision about whether or not to trust things like government and financial institutions and or new digital financial technologies. There are obviously occasions here when this trust may be misplaced or ill-advised, and I think it's similarly instructive to think here of an ongoing arms race between new computational developments and the new forms of cryptography that may ultimately be required. So I think it's unlikely that you're going to get to a stage where you've got one computational system like a blockchain which is completely immune to hacking. I suspect that there is always going to be this sort of fundamental evolution between those who create new systems and those that seek to hack it, and there's going to be a fundamental need for emotional judgments around trust.